So you don't sample this particular pin again during that delay. Another thing, a question I was asked yesterday was about, well, how can you tell the difference if someone's holding on to a button or whether they're pressing it multiple times? Again, we could use a similar kind of technique with that, but having had a transition, whether it's got bounce or no bounce whatsoever, we set a flag and say, or a transition has taken place. Until we sample it again and it's back up here, we ignore the fact that it's still down here. So effectively, what you're doing is you're noticing when it goes low, but it's effectively the high to low transition that you're recording is actually the key press. And these two things could be combined with the same bit of software here. So what would happen is you're sampling this pulse, this pin. If it's high, you assume nothing's happened. When it goes low, you basically set a flag saying, oh, the key's been pressed. You go into a little delay loop, twiddle your thumbs for a little bit. After that, you can go back and sample it again. If it's gone high again, you're ready to sort of, the next time it goes low, you know it's basically a fresh pulse. If after the delay loop it's still reading as low, you basically say it's still the same key press. Don't treat it as a separate key press. So a software delay loop is one way of doing it. Now how big or how small should that delay loop be? It's really down to the designer. You've got to think, well, just how fast can a human being sort of press a button? And maybe you're playing games on a gamepad or something, and maybe you expect to be quite quick. But probably, a few milliseconds delay is all you need in order to deal with this contact bounce. An alternative is this thing called the Schmidt trigger, and effectively, let's see if I can draw this right. I wouldn't draw this down yet until I'm convinced I've done it right. So, if the input goes from low to high, well, while the input's low, the output might be low, for example. When the input gets to a certain amplitude, then the output will go high, so it will kind of go up here. But if the output's high, then even if the input lowers, the output will stay high until a certain threshold is reached, and it will drop back down like this. And this is known as a hysteresis loop. So what it's saying is on the kind of upward path, we go this way, we go that way, the downward path. So when the input's low, the output's low, for example. The input's getting higher and higher and higher. Crosses this threshold, nothing happens. It has to become way high up here. At that point in time, the output goes high, which is why we're up here. Now, if the input starts to get lower again, if it was a classic buffer, you'd get something that looks like this. Loads of pens today. A classic buffer would look just like that. No hysteresis. There'll be some kind of threshold that when you cross it, the input gets above a certain level, the output goes high. When on the way down, you get to that same level on the input, the output will drop. So the output is directly dependent on the input voltage. And there's just a particular point where that crossover takes place. In a Schmidt trigger, when the input exceeds a certain value, the output goes high, which brings us up here. But when the input starts to drop again, the output isn't dropping, the output is staying high until this lower point, this lower threshold is reached, and then it will drop back down. That allows you to deal with these kind of little wobbles here, that these would not be sufficient usually to trigger it to make the output change again. So the input to the Schmidt trigger would look like that. The output, it would see these, but these pulses wouldn't be high enough to trigger the output to change state again. You'd be somewhere along this line here. So that's the other way that we normally deal with contact bounce in switches. So You can do either of two things. You can have a little delay loop and make basically your circuit unresponsive to changes in the input, having had a transition for a certain period of time. Or alternatively, you have your input connected, not directly like this, but you have a little Schmidt trigger or something here. You can see, by the way, this is why we go to Schmidt trigger. It's like an ordinary buffer. They've got a little hysteresis loop shown on the symbol to show it's not just an ordinary buffer, it's a special buffer, it's a Schmidt trigger. So you could put one of those there, and then you don't need to worry about your software delay loop. These like little short-term spikes that may have otherwise triggered you to think that the input's gone high again will be ignored. Now, if they are more than a certain amplitude, it will trigger. But it does actually improve false triggering quite considerably. The downside, of course, is you're having to pay for another integrated circuit connected to your microcontroller. Some members of the 8051 family do have Schmidt triggers built into some of their inputs. And you can actually, under software control, say whether you want the Schmidt trigger to be active or to be switched off. Okay. Let's move out of the way. Yeah?
Are they variable? You buy them set that?
They're pre-defined. You can't set the thresholds now. You could probably, be using op amps, design yourself the equivalent of a kind of one where you could adjust the thresholds, but you're not the Schmidt trigger, it's kind of predefined. Okay, so 7-segment displays, and I apologise that most of you have done lab 3 before we've had a kind of got onto this. I suppose lab 3 should have started in week 10, not week 9. Anyway, we'll quickly whiz through different types of display. Perhaps some of it might still be useful for your design and build projects. So what can I say? Well, there's lots of different types of display out there. There are old things called Nixie tubes that you've probably never come across. There's LCDs, liquid crystal displays, and LEDs, light-emitting diodes. The advantage of an LED display is it's actively generating photons itself, so you can use it in the dark without any problem. With an LCD display, it's just changing the polarization of light, so it works fine in sunlight, but in a darkened room, you have a problem unless you paid that extra 10p or whatever for a backlit LCD that has illumination behind the screen. Okay, 7-segment LEDs. There is a standard sort of convention about how we label the LEDs working around clockwise. So A, B, C, D, E, F. These are called the segments. And it's a 7-segment LED, but actually there is an 8th LED here, which is the decimal point if you choose to use it. And you can buy these as little gadgets. They're relatively cheap. Nothing particularly exciting there. And they're usually wired up in one of two ways. It doesn't particularly matter which option you go for, but you need to know that. The 8 LEDs are either wired up so that their anodes are connected together, or they're wired up so that their cathodes are connected together. So we talk about them being common anode or common cathode. Some LED driver modules will assume that you're using one type and not the other type. So it's fine if you're simply, if this was just connected to a microcontroller and you wanted to make these come on, then you could have this, for example, connected to ground, and then when you had a high voltage on any of these, that particular light will come in. In this particular case here, you could have this connected to VCC, and then each of these would be going to one of the pins on the microcontroller. When the pin goes low, the LED would come on. So either way is possible. You might argue that in some ways this is a better alternative because you're sinking the current into the microcontroller, but common cathode is fine as well. Okay. The problem if you're driving them directly from a microcontroller is there's no intelligence in those little 7-segment displays in themselves. So if you've got a particular module with its various segments, decimal point or whatever, effectively you're wiring up pins on the microcontroller to each of these things, and the other end of these is all being wired to a common point, for example. You've got to keep using that pin on the microcontroller and not change its state, because changing its state would actually change whether these LEDs are on or off. Which is fine if you've got lots of spare pins on the microcontroller. The pins on the microcontroller have latches associated with them, so not a problem. However, there are other alternatives as well, and this is an example where this is basically doing some kind of decoding for us. Now, in this particular case, if you're just driving this display yourself and you want it to represent the number 6, for example, so in one of your registers you've got the number 6 and you want it to display 6, well, you can't just write 6 out. You're going to have to work out which segments to light in order to produce the number 6. So you're going to have to do some kind of conversion between the numerical value, i.e. 6, and which segments need to be eliminated in order to represent that numerical value. Which is not that difficult, but it is some work that your microcontroller has to do. An alternative is this type of device here. That 4511, where effectively what we've got here is we're presenting the numerical value into this place which is being latched, and then that's being decoded, that's what this is doing, so that the appropriate display segments are lit based on that numerical value that's been held in the latch. So you don't have to worry about doing the conversion. You just simply say, oh, I want the number 7, so you basically write out binary 7 here. That will be latched in here, decoded, and then the appropriate segments will be illuminated in order to provide something that looks like a 7. This can be quite useful because we could actually do multiplex displays with this type of thing, by the way. Where I could have the same pins going to a number of latches, with a separate latch enable acting as like address decoding. So, it's that kind of blank look at some of your faces. Effectively, I could have a number of these devices where the 4 wires that are going to this one are also going to these others. Not sure I've wired it up correctly, whatever. And it's true I need some additional pins, but I could use some additional pins to either enable this one or to enable this one. Oops, don't do that. That's a pin. Or enable this device. Then effectively this is acting as a kind of bus where I write out the value, lock it into here, but the other ones won't necessarily get the new value because I'm only enabling one of them at a time. The other ones will just hold on to the value that they had before. If I didn't use this multiplex technique, then effectively, at the very least, I'm going to need 12 pins for my 3-digit display, 4 for each one. But I've multiplexed these lines, so instead of 12, I'm only using 7 lines. And the nice thing about this is the ones that I'm not updating, because of the latch, they'll hold on to their existing value.
Well, that's no problem.
You'll all have done this from the lab anyway, but in the case of the lab, we don't have any intelligent external integrated circuit, but we are using this thing called a multiplexed LED display. And so we're achieving something that looks like all the digits are on by effectively only switching 1 digit on at a time, but changing that. So if we want to display the number, I don't know, 1, 3, 5, 7 on this display, Effectively, on the top side of it, I've got my segment bus, which is going in parallel to all the devices. If we're not using decimal point, then that's going to be 7 bits wide, 7 lines. And then on the other end of the device, we're basically having 4 more lines which are controlled by the microcontroller. So the microcontroller is sitting over here. 7 lines of microcontrollers used here, and a further 4 lines are used here. And then the idea is, now in this particular case I want to display this number, so how do I achieve that? Well, first of all, let's assume these are going to go high when we want that particular segment illuminated. Down here, effectively I'm going to write 0, 1, 1, 1. And I make the segments go high here. I want to be illuminated. So in this particular case, it will be that segment and that segment. So those lines would go high. These would light up because basically we're going from a high potential through the LEDs down to ground. Now, it's true that those particular LEDs will also see that high voltage here and here and here and here and so on, but their other end of these things, the common terminal, is not going to ground, it's kept at high voltage, so there's no potential difference across those other ones, so they will not illuminate. Having done that, then I want this to illuminate. Effectively I have to switch this off, and then I write out the pattern. So that would be the pattern I'd write out when I'm doing the number 1. When I'm doing the number 3, I would write out the pattern, this one, and then write a 3 out on this bus, the segments for that one, which would cause this to illuminate, but not in any other digit. And then I repeat the process for the 5 and the 7. So what you're really displaying across your, over time, so this is time, you're going to write a 1 here first of all, then you're going to write a 2 here, then you're going to write, oh, sorry, not a 2, so in our case, a 3, 5, and then a 7. That's all that's ever illuminated. But if you cycle through this process enough times, it will appear as if you're writing 1, 3, 5, and 7. We rely on the fact that the human eye, the chemicals and the photoreceptors at the back of the eye take time to disperse or whatever, so you get this kind of persistence of vision effect. So even though this has been extinguished, your eye doesn't see it disappearing straight away. And if you cycle through this process quick enough, you get the perception that all of the digits are illuminated all the time, even though they're not. If you want to change the brightness of the display, you can change the ratio of the time that the digit is illuminated to the time when no digits are illuminated. So if it's only for a brief time, then it's off for a while, and that's on a brief time, and it's off for a while. That's on for a brief time, and then it's off for a while. That's on for a brief time, and then off for a while. It will look like a dim display. Whereas if you have this on, and then you keep it on all the time until it's time to switch this one on, and so on, that's about as bright as you can get it.
Sweet.
Okay, so in fact, that's that pointer at the top up there. So you can adjust the brightness by altering the on-off ratio, and provided you cycle through all the digits in 50 Hertz or more, most human beings can't tell that it's flickering anymore. You might still notice it if your eyes scan across it, but if you're just looking at it, it will look like it's just a solid display. In addition to saving pins by designing circuits like this, there is another advantage. We're actually only illuminating 1 digit at a time. So if you've got a battery-powered system, that's quite an energy saving because you're not lighting up all the digits. At any point in time, only one of them is being illuminated. So another benefit of using a multiplex display. And this is saying unless you have separate circuitry we are giving the microcontroller a lot of work to do. Yeah?
The on-off ratio, is that the same as positive modulation?
It's doing exactly the same kind of thing, yes. Here's, it's exactly the same circuit as this one, but this is the slightly more, the kind of Rolls-Royce version of it, where, in fact, we're not putting too much strain on the microcontroller. This is out of the book, and it's doing exactly what I've shown you down here, except the segments are not being illuminated directly by the pins now. They're being used to switch on and off transistors, which are illuminating the various segments. And then the other pins, which basically act as the sinks, we're not doing that directly into the microcontroller. We're using another block of transistors here, which are acting as the switches at the bottom to decide which of the digits is illuminated at a time. Other than that, it's exactly the same setup. The nice thing about this is that when this is, for example, the segment's illuminated here, the brightness of the segment during the period of time it's illuminated is governed by that little resistor up there, so you could actually have quite a bright display. Other than that, nothing else on that slide. Compared to just having these 7-segment displays directly controlled without any kind of multiplexing from the 8051, you're talking about this would take 28 pins on the microcontroller. Whereas using this technique, we've dropped that down to, well, we've got 8 up here. In fact, I think we're using, no, we're using 7 of the pins up here, because we're not using decimal point, plus the 4 things here. So 11 as opposed to 28 pins. That came up one year in an exam question about describing how that circuit worked. But I'm assuming that you're all quite happy with the operation of that. Logically, it's doing exactly the same thing as over here. Okay, let's move on briefly now, because we've still got one whole topic to do. We've only got 2 days, 1.5 days left on this course. And I still want to say a few words about revision. So, LCDs. LCDs, most of them follow, have a common interface. 14-pin interface. Now, okay, there may be some kind of wacky ones out there that you can buy that don't use this standard interface, but most of them do. Okay? Now, the pins on that particular interface look like this. I wouldn't expect you to remember any of the details. So we've got 8 data lines. We've got a read-write signal and an enable signal. We've got 2 registers effectively inside the LCD display. One of them which is a control register that you use for configuring it. And then when it's in data mode, then whatever you write to it, it gets written, will actually be displayed. Yeah. Okay. And then there's just several voltage lines here. One of them is, allows you to effectively adjust the contrast between VDD and BSS. Okay? So the register select line, if it's low, you're talking to the internal control register. If it's set high, you're talking, basically you're writing to the actual display itself, writing the data. This is taken from a data sheet somewhere, showing you the sequence of steps that you go through in order to write to an LCD display. So if we look at this briefly, in this particular case, you can see that the register select line is going low when we're doing something interesting here. So we're obviously trying to write to the control register. The sequence of steps, if you had to write a little bit of assembly language to do this, is first of all, we've decided we're going to do a write operation. So this line's going low. At the same time, we've decided which register we want to talk to, i.e. the control register. And then we have to wait a little bit of time until we fiddle around with this enable signal. And the manufacturer says that that time has got to be, in this case, 140 nanoseconds. Well, if you've got a 12 megahertz 8051, and you're using, it's a classic 8051, that's 1 microsecond per instruction, which is 1,000 nanoseconds. So you wouldn't need to worry about that. Okay? Basically, you would make these go low, and then straight away after that, you can make that go high. there's now another, we set up the data that we want to write to the control register. And then, having made that go high, the enable pulse has to be kept high for a certain minimum period of time, which I think in this case is 450 milliseconds, about half a microsecond. Again, shouldn't be a problem for us. If you're using a fast member of the 8051 family, or some other processor, where the machine cycle time is less, then you do have to bear this in mind. Because if you basically, I'm going to say exceeds the wrong way around, if you don't hold it for this minimum period of time, the operation of it will malfunction. It won't necessarily latch in the data. The actual latching operation in this case, interestingly, is actually taken from the enable pulse. It's the transition from the high to the low on the enable pulse is actually when the data gets locked into the device. Having made that transition, there's another period of time that we have to wait, a hold time, before we can start fiddling around again. And this, you can see this period of time here, TH, that's saying that has to be 10 nanoseconds in that case. And from the point of that transition from a high to low here, you've got to make sure that the read-write signal is still kept in the same state for a further 140 nanoseconds. Sorry, is that no, AH, another 10 nanoseconds. So again, with a classic 8051, provided you do the right sequence, you don't have to worry too much about the timing. However, it would appear that effectively, based on the timing information that I've just given you, with a classic 8051 that takes 1 microsecond per machine cycle, you could happily write to this, provided you follow this sequence as fast as you like, give or take. In theory, you could say, oh, I can write about 1 million characters to this display a second, no trouble. What this diagram does not show you, and it's probably buried elsewhere in the data sheet, is having performed an action, often LCDs have a kind of a period of time where they're doing things internally that you have to wait for, and those times are appreciable. For example, in the case of if you want to blank the display, from the time you do that to do something else, the recommended time is 2 milliseconds. A lot of actions when you're writing characters, having written a character to the display, there's until you can write the next one, there's usually about, I think it's 140 microseconds. Or, sorry, about 40 microseconds, not 140, 40 microseconds, which is 40 machine cycles. So if you just try and write hello world or something straight away to the display, observing just these timings, it may not work. What you need to do is you write one character, then you have to wait for this other period of time until it's time to send the next character and so on. Now, you can either read the data sheet and make sure you put a little delay loop in to space out when you're doing these different operations, or alternatively, D7 usually on the LCD display, once you've performed a writing operation, it will go into a certain state. It usually goes high, I think. You can read that back. When it's finished the operation, it's ready for the next operation, it changes state. So you can use it as a kind of handshaking signal to work out how fast you can write to it. None of that you need to know for this course, okay? You're not going to be tested on the details of an LCD display. I'm only mentioning this in case any of you, I know it's getting close to the end of your design and build projects, but if any of you are using LCD displays and having trouble writing to them, be aware of these kind of timing issues. And the main timing issue that matters is, having done one thing, how long do you have to wait until you can do the next thing? And that time could be quite long. Okay, so this is now talking through step by step if you wanted to write a particular thing, what you do. So normally you would write to the control register. When you power up an LCD display, normally it's in blank mode, so you have to enable the display. So that's usually the first thing you want to do. Having enabled the display, effectively you switch to the data register to write your character. One of the features of LCD displays is it uses a technique called auto-incrementing.